we will continue to solve examples of magnetic circuits. This is another example in which we have a ferromagnetic core whose mean path length is 40 centimeters. So the length of the whole core is 40 centimeter. Gap is 0.05 centimeter. The air gap here. And the cross-sectional area of the core is 12 centimeters. So they have given the cross-sectional area. Relative permeability of the core mu r is 4000, and the coil that is wrapped here has 400 turns. They have mentioned that the fringing exists here, so we have to consider fringing effect. And what fringing is causing? Fringing causes an increase in the cross-sectional area as the flux bulges out. So there will be a 5% fringing effect here. And with all this information, we have to find the total reluctance RT of the core and the current required to produce a flux density. And we need to find the current I, this current, which will produce a flux density of 0.5 Tesla. So the first step and the basic step should be, first we should try to make the magnetic equivalent circuit for the given core. So what will be the equivalent magnetic circuit? We can see that we have a core here, we have a source here, we have single source, and there are now two types of reluctances that are hindering the flow of flux. Number one is the flux of the core, reluctance of the core, sorry, and the second one is the reluctance of the air gap. So we have two types of reluctances. And here a flux will be flowing. Here the force is F equals to Ni. N we know, but I we don't know. So how to solve this? The first part says that we have to calculate the total reluctance of the core. So let's look at here. Let's change the color to calculate the reluctance. So first we calculate RC. So what is the formula for RC? RC is LC mu over AC, area of the core. Now what is the LC? In this case, it is 40 centimeter and 0.05 centimeter is very low. So we'll almost neglect it. Actually, the real mean path length is 40 cm minus 0.05 cm. But this we can, or it is almost equals to 40 cm. So and remember, we have to put the values in meters. Mu is actually mu naught into mu r. Mu naught we know is 4 pi into 10 raised to the minus 7. Mu r they have given to us, that is 4000. So this will actually become 4 pi into 10 raised to power minus 7. And what is mu r? It is 4000. N is AC. The area of cross section is, they have given us, it is 12 centimeter square. In meters, it will become 12 into 10 raised to power minus 4. So we can write here 12 into raised to power 10 minus 4. And so the reluctance of the core RC will become equals to approximately 66,300 ampere turns per Weber. Now to calculate the area of R gap, to calculate the reluctance of the air gap, it will be length of air gap divided by mu into area of air gap. Now to understand this, the length of the air gap they have given to us, that is actually 0.05 centimeters. That will be equal to 0.0005 meters. So students, be very, very careful. Often students make mistakes because there are many decimal points. For mu, we know that it is air gap. So mu naught equals to, it will be actually equals to mu naught, where relative permeability is equals to 1. And about the air gap, now air gap, it states that it has a fringing effect. So fringing effect causes a 5% increase. So originally the area was 12 centimeter, and due to fringing we had a 5% increase. So the area will become 12.6 centimeters square. That will be actually 12.6 into 10 raised to power minus 4 meters square. So if now we perform the calculations, this the area, the reluctance of the air gap will become Ra is equals to, let's do it here, and so Ra equals to, yes, if you solve it, now the important things to note, look at the difference in the reluctance of the air gap and of the core. The whole core is 66,300 and a very small air gap has such a high reluctance. So now we can calculate our RT, and RT we know that RT is equals to RC plus RA. RC we have calculated, RA we have calculated. The total reluctance of the core will become 3000 divided by 300 ampere turns per Weber. This is the first part, and we have calculated this as the total reluctance. Now they are asking for the current also. So let's look at few basic equations. Now we have calculated the flux. Now they are asking about this current. We have calculated, we have not calculated total flux, we have calculated the total reluctance. And now we have to calculate the total current. So the basic equation we know for MMF is F equals to omega R, and F equals to phi R, and where R is the total reluctance. So they have given us flux density, that is actually equal to this value, flux per unit area, or we can put these values, and we also know F equals to Ni, so we can rewrite this equation equals to B A R, or I equals to B A R T over N. So let's look at what values we have. We have the value of 0.5 Tesla, we have the area, and now which area, that is important. We have two areas now. We have the area of the core and area of the air gap. So what is they are saying? The current required to produce a flux density of this in air gap. So we are talking about the air gap. So here the area is this area of the air gap. Reluctance we have calculated. Here is the total reluctance, 300 impedance per Weber, and the number of turns we know is 400. So the value of I, if you calculate from by substituting all the values, will be 0.602 amperes. This will be the value of your current. And one important thing I would like to add, that the flux remains the same through the core as well as the air gap. same number of lines, flux lines, magnetic lines will be flowing through the core and also through the air gap. What changes is the flux density because the cross sectional area is changing. So if flux that is flowing through this line, if for example 1 Weber flux is flowing through the core, same flux line will also flow through the air gap, but only they will bulge out, so their area will increase but the flux will remain same. Okay, students, I hope it helps. Thank you.